IP address. As we know, as we learned before, to send a message, send an information, or open the web page, we need an IP address of the remote computer, of the friend's computer, of the website. Maybe we don't know the exact IP address, but our computer knows that because it communicates with a remote computer. So what is IP address? An Internet Protocol address, or IP address, is a numerical label assigned to each device, for example, computer, printer, or other network device participating in a computer network that uses the Internet Protocol for communication. An IP address serves two principal functions: host or network interface identification and location addressing. Its role has been characterized as follows. A name indicates what we seek. An address indicates where it is. A route indicates how to get there. The designers of the Internet Protocol defined an IP address as a 32-bit number, and this system, known as Internet Protocol version 4, IPv4, is still in use today. However, due to enormous growth of the Internet and the predicted depletion of available addresses, a new version of IPv6 using 128 bits for the address was developed in 1995. IPv6 was standardized as RFC 2460 in 1998, and its deployment has been ongoing since the mid-2000s. We'll talk about IPv4 addresses because IPv6 is more complicated, and we will spend more time to discuss it. But at first of all, we need to discuss and understand the principles of IPv4. The Internet Assigned Numbers Authority, IANA, manages the IP address space allocations globally and delegates 5 regional Internet registries, RIRs, to allocate IP address blocks to local Internet registries, Internet service providers, and other entities. IPv4, an address, consists of 32 bits, which limits the address space to 4,294,967,296. Oh, it's too big. Possible unique addresses. IPv4 reserves some addresses for special purposes, such as private networks, approximately 18 million addresses, or multicast addresses, and multicast addresses are 270 million addresses. IPv4 addresses are canonically represented in dot decimal notation, which consists of 4 decimal numbers, each ranging from 0 to 255, separated by dots. Each part represents a group of 8 bits, octets, of the address, in some cases of technical writing. IPv4 addresses may be presented in various hexadecimal, octal, or binary representations. In the early stages of development of the Internet Protocol, network administrators interpreted an IP address in 2 parts: network number portion and host number portion. The highest order octets, most significant 8 bits, in an address was designated as the network number, and the remaining bits were called the rest field or host identifier and were used for host numbering within a network. This early method soon proved inadequate as additional networks developed that were independent of existing networks already designed by a network number. In 1981, the Internet Addressing Specification was revised with the introduction of classful network architecture. Classful network design allowed for a longer number of individual network assignments and fine-grained subnetwork design. The first 3 bits of the most significant octet of an IP address were defined as the class of the addresses. 3 classes A, B, and C were defined for universal unicast addressing. Depending on the class derived, the network identification was based on octet boundary segments of the entire address. Each class used successively additional octets in the network identifier, thus reducing the possible number of hosts in the higher order classes B and C. The following table, as you can see on your screen, gives an overview of this now obsolete system. Here, as we can see, the first octets shows in class A the network number, and it varies from 0 to 127. Other 3 octets in class A are used to identify the host. Those who will have 128 networks and over 16 million hosts in class A network. In class B, we have first 2 octets used for network, and the first octet digits should be in range within starting from 128 and ending with 191. The rest 2 octets will be used for host. Thus, we will have approximately 16,000 networks and 65,000 numbers of addresses per network. Class C shows in Class C first 3 octets identifies the network, showing the network number and the first octet should start from 192 to 223. Thus, the last digit will show the host number, host identifier, and we will have approximately 2 million networks and 256 hosts in each network. Classful network design served its purpose in the startup stage of the Internet, but it lacked scalability in the face of the rapid expansion of the network in the 1990s. The class system of the address space was replaced with classless interdomain routing in 1993. Classless interdomain routing has its own abbreviation, CIDR. It's based on variable length subnet masking, VLSM, variable length subnet masking, to allow allocation and routing based on arbitrary length prefixes. Today, remnants of classful network concepts function only in limited scope as the default configuration parameters of some network software and hardware components, for example NAT masks, and in the technical jargon used in network administrators' discussion. Early network design, when global end-to-end connectivity was envisioned for communications with all Internet hosts, intended that IP address be uniquely assigned to a particular computer or device. However, it was found that this was not always necessary as private networks developed and public address space needed to be conserved. Computers not connected to the Internet, such as factory machines that communicate only with each other via TCP/IP, need not have globally unique IP addresses. 3 ranges of IPv4 addresses for private networks were reserved in RFC 1918. These addresses are not routed on the Internet, and thus their use need not to be coordinated with an IP address registry. Today, when needed, such private networks typically connect to the Internet through Network Address Translation, NAT. Any user may use any of reserved blocks, any of reserved addresses. Typically, a network administrator will divide a block into subnets. For example, many home routers automatically use the default address range of 192.168.0.0. IPv4 address exhaustion is the decreasing supply of unallocated IPv4 addresses available at the Internet Assigned Numbers Authority (IANA) and the regional Internet registries for assignments to end users and local Internet registries such as Internet service providers. IANA's primary address pool was exhausted on 3rd February 2011, when the last 5 blocks were allocated to the 5 rears. APNIC was the first rear to exhaust its regional pool on 15th April 2011, except for a small amount of addresses space reserved for the transmission to IPv6, intended to be allocated in a restricted process. IP networks may be divided into subnetworks in both IPv4 and IPv6. For this purpose, an IP address is logically recognized as consisting of 2 parts, the network prefix and a host identifier or interface identifier in IPv6. The subnet mask determines how the IP address is divided into network and host parts. The term subnet mask is only used within IPv4. Both IP versions, however, use the CIDR concept and notation. In this, the IP address is followed by the slash and the number of decimal or bits used the network part, also called the routing prefix. For example, an IPv4 address and its subnet mask may be 192.0.2.1 and 255.255.255.0 respectively. The CIDR notation for the same IP address and subnet is 192.0.2.1/24 because the first 24 bits of the IP address indicate the network and subnet. IP addresses are assigned to a host either new at the time of booting or permanently by fixed configuration of its hardware or software. Persistent configuration is also known as using a static IP address. In contrast, in situation when the computer's IP address is assigned newly each time, this is known as using a dynamic IP address. Static IP addresses are manually assigned to a computer by an administrator. The exact procedure varies according to platform. This contrasts with the dynamic IP addresses, which are assigned either by the computer interface or host software itself, as in zeroconf, or assigned by the server using Dynamic Host Configuration Protocol. It's a DHCP. Even though IP addresses assigned using DHCP may stay the same for long periods of time, they can generally change. In some cases, a network administrator may implement dynamically assigned static IP addresses. In this case, a DHCP server is used, but it is specifically configured to always assign the same IP address to a particular computer. This allows static IP addresses to be configured centrally without having to specifically configure each computer on the network in a manual procedure. Of course, DHCP server will differ the different computers, will separate them using the address which we called MAC address, Media Access Control address. So we need to identify the different computers and assign them the different IP addresses. If we will assign the same IP address or configure the same IP address on a different computers, for example, on two different computers, IP conflict will rise. It will write on the ARP or MAC cache that the same IP address with different two MAC addresses exist in MAC table. Thus, the connection will be unavailable. I will show you a cute experiment from my own practice where you can see how you can set the IP addresses where I set the IP addresses, the same IP address to two computers, and there were no any conflict. It was from my own practice, and I'll show you a little bit later. Dynamic IP addresses are most frequently assigned on LANs and broadband networks by Dynamic Host Configuration Protocol (DHCP) servers. They are used because it avoids the administrative burden of assigning specific static addresses to each device on a network. It also allows many devices to share limited address space on a network if only some of them will be online at a particular time. In most current desktop operating systems, dynamic IP address configuration is enabled by default so that a user does not need to manually enter any settings to connect to a network with a DHCP server. DHCP is not the only technology used to assign dynamic IP addresses. Dial-up and some broadband networks use dynamic IP address features of the point-to-point protocol. There are sticky dynamic IP addresses, which are the informal terms used by cable or DSL internet access subscribers to describe a dynamically assigned IP address which seldom changes. The addresses are usually assigned with DHCP. Since the modems or routers are usually powered on for extended periods of time, the address lists are usually set to long periods and simply renewed. If a modem is turned off and powered up again before next expiration of the address list, it will most likely receive the same IP address. RFC 3330 defines an address block 169.254.0.0/16 for special use of link located addressing for IPv4 networks. You can see this IP address when you are connecting to a switch which is not connected to anywhere. At first, your computer will search for a DHCP server. If there is no any DHCP server, it will assign random IP address from this range, from 169.254.0.0/16. These addresses are only valid on the link such as local network, segment or point-to-point connection that a host is connected to. These addresses are not routable and, like private addresses, cannot be source or destination of packets traversing the internet. When the link local IPv4 address block was reserved, no standards existed for mechanism of address auto-configuration. Filling the void, Microsoft, which product Windows you are using, created an implementation that is called automatic private IP addressing. Due to Microsoft market power, this mechanism has been deployed on millions of machines and has thus become de facto standard of industry. Many years later, the IETF defined a formal standard for this functionality. RFC 3927, entitled Dynamic Configuration of IPv4 Link Local Addresses. Some infrastructure stage situations have to use static addressing, such as when finding the domain name systems host that will translate domain names to IP addresses. Static addresses are also convenient but not absolutely necessary to locate servers inside an enterprise. An address obtained from a DNS server comes with a time to leave or caching time, after which it should be looked up to confirm that it has not changed. Even static IP address do change as a result of network administration.